The objective today is to explain why encryption is an important need for everyday life on the internet. The most important aspect of this lesson is to understand how and why encryption plays a role in our lives every day on the internet, and that making good encryption is not trivial. Students will get their feet wet with understanding the considerations that must go into making strong encryption in the face of powerful computational tools that can be used to crack it. The need for secrecy when sending bits over the internet is important for anyone using the internet. In this lesson, students are introduced to the need for encryption and simple techniques for breaking or cracking secret messages. Students try their own hand at cracking messages encoded with the classic Caesar cipher and also a random substitution cipher. Students should be well acquainted with the idea that in an age of powerful computational tools, the techniques of encryption will need to be more sophisticated. So my think, write, share here is predict what do you think cracking encryption means? This lesson is the first in a series of lessons about cryptography and encryption. Now, encryption is a process for transforming a message so that the original is hidden from anyone who is not the intended recipient. Encryption is not just for the military and spies anymore. We use encryption every day on the internet, primarily to conduct commercial transactions, and without it, our economy might grind to a halt. Think, write, share in your own words. What is encryption? Computational tools dramatically increase the strength and complexity of the algorithms we use to encrypt information, but these same tools also increase our ability to crack encryption. Developing strong encryption relies on knowledge of problems that are hard for computers to solve, and using that knowledge to encrypt messages. Think, write, share what could possibly be difficult for a computer to do. And I give you a hint here, are you a robot? And below here is a nice visual for you to look at. You have your plain text, maybe a social security number, and you add a key and an algorithm to it. It turns it into a ciphertext. Now, the company or whoever you're sending this information to would then get that cipher. They'll need a key themselves and an algorithm themselves to transfer it back into something that's readable. Your think, write, share here is in your daily life, what things do you or other people rely on keeping secret? Who are these secrets being kept from, and how are these things kept secret? And this is these things that you are talking about in your answer to the first question. And here's a nice infograph for you. It says here about 198 cyber attacks happen a year in terms of hitting critical U.S. infrastructure. That is to say, water, energy, government facilities, chemical and nuclear plants. Now, 90% of cybercrime is due to malicious code, denial of service, stolen or hijacked devices. So these are the types of things we're talking about when we say cyber attacks. And then the 10% would just be other types of attacks. You have 45 days as the time it takes an average person or company to contain an attack. And here's your average price of an attack in terms of having an 18-day period. The time period could be more, and thus the price would be more. But again, it's an average price over 18 days. And according to this infograph, it's 2012 IT World created, and there's some sources that they use. We are scoring a 3 on a scale from 1 to 10 in terms of American preparedness for major cyber attacks. Secrecy is a critical part of our lives in ways big and small. As our lives increasingly are conducted on the internet, we want to make sure we can maintain the privacy of our information and control who has access to privileged information. Digital commerce, business, government operations, and even social networks all rely on our ability to keep information from falling into wrong hands. Over to the right, 28% of organizations view cyber insurance as a substitute for cyber defense. This is a really bad thing. Just because I pay car insurance doesn't mean that's a substitute for me driving safely. I still drive safely, even though if I do get in a car accident, that will be paid for by the insurance company. The fact that the number is 28% is insane. That's too high. Recall some of the facts we learned in Unit 1 while using that internet simulator. The first fact I want you to recall is the fact that the internet is not inherently secure. The second one is packets traveling across the internet move through many routers, each of which could be owned by different people or organizations. Can you remember the organizations that we talked about who own the internet? The third one is we should assume all information traveling across the internet is public, as if it was written on a postcard and sent to an unlocked mailbox. Now in my neighborhood, my mail is actually locked, which is nice, but there's lots of neighborhoods across America where the postman or woman will put the letter in a box that is completely unlocked, and mail theft does happen. What I'm saying here is, with the third fact, we should pretend as if the things we do and say on the internet possibly can be seen or taken by other people. And so this is where encryption comes in. This is supposed to try to protect us from getting that information stolen. It says encryption is a process, aka an algorithm, for transforming a message so that the original text is hidden from anyone who is not intended to receive it. This is often called a secret code. Now, reversing the encryption process to reveal the original message is called decryption. History is full of examples of people encrypting messages and attempting to crack secret codes. So the point is, in history, people were encrypting things long before computers existed. All right, so first I want you to just have fun with this link and play around with the frequency in this substitution exercise. I'll go ahead and post the link on the Canvas for those of you who are in my class. For everyone else, go ahead and just type that in. And your task today is to finish bubbles 4 through 6 once you get here. So here we are on the link, and it's actually bubble 2 that I'm starting on because I want to explain to you a little bit about how a Caesar cipher works. Let's say this is a message that you want to hide. Now, a Caesar cipher, what this does is it will scramble these letters into something that is very hard to understand. So if I come down here and I click the right arrow, it will shift the substitutions to the right by 1. So now it does look jumbled, and I can shift it more, and you can see it keeps changing right there on the top left. When you go to the next screen, there will be some vocabulary words there for you, and then just click past that to get to number 4 here. Again, I want you to get 4, 5, and 6 done. So read the words here and then move on to the next part so you can accomplish these tasks. If I do it for you here, I don't think you'll be learning as much as if you attempted it on your own. But for those of you in my class, I'll be around to help, of course. So a big takeaway from that exercise is understanding frequency analysis. It says the best technique for cracking a random substitution cipher, a substitution cipher such as the Caesar cipher, is known as frequency analysis. What this does is it's a technique that is based on how frequently certain letters appear in English versus other languages or other letters. So for instance, given a section of English text, E, T, A, and O are the most common, while Z, Q, and X barely show up. Likewise, T, H, E, R, O, N, and A, N are the most common pairs of letters that occur next to each other. In fact, the distribution of letters is roughly the same for almost all samples of English text. So it's relatively easy to figure out what that cipher text can be translated into. All you have to do is basically break apart a single word and figure out what the shift was. Then you can use that number on the rest of them. So in your own words here, think right here, what is frequency analysis? By analyzing the frequency of letters in the encrypted message compared to the frequency of letters in a typical piece of English prose, you can start to narrow in on what some of the letter mappings might be. The tool shows you how the frequency of letters in the encrypted text, which is the orange part, compares with the frequency from typical English letters, which is in blue. You think right here, are you comfortable with the term mapping? Basically, it's just like encoding, so do you remember encoding well? So we're almost done here. Just some vocabulary, what encryption is, what decryption is, what a cipher is. I don't think I addressed this specifically. So a cipher is the term for a technique that performs an encryption. So there's different techniques and thus different ciphers. The Caesar cipher is the one we specifically studied today. The beginning of the lesson, you were asked how or what cracking encryption could mean. Here it says when you attempt to decode a secret message without knowing all the specifics of the cipher, you are trying to crack the encryption. So think, rate, share. Please put these words in order from easiest to understand to hardest. One more think, rate, share, and then we're done for the day. Knowing what you know about frequency analysis, would you feel comfortable sending your password over the internet using a substitution cipher? Why or why not? And try to go as deeply as you can with this question. Think about what I was just telling you about frequency analysis and common words that pop up, common pairs that pop up. Is your typical password that you've created, or maybe the password that the school has given you, do you think that it would be easily broken or deciphered with frequency analysis, or would it not? So the last thing to do is choose one of the IB profile attributes to connect to today's lesson. And then here we are at the DOL. It says, Batman wants to send a message to Wonder Woman without Brainiac intercepting it and decrypting the information. If this message simply shifts each letter to the right by 3 positions, what type of cipher is he, Batman, using? And how easy would it be for Brainiac to decrypt this message? Pretty easy DOL, and I think it was a pretty easy lesson. Next time we'll go more into the mathematical details of how encryption algorithms work.